Welcome to Maths with EJD. In this video, I'll be talking about advanced mathematical tools and theorems in harmonic analysis, and that is still under Fourier series. In fact, this should be about the last video on Fourier series. All right. In the previous video, I talked about harmonic analysis and how that is connected with Fourier series. So let's go into this. Advanced mathematical tools in harmonic analysis include powerful theorems and transforms that extend the capabilities of basic Fourier analysis. Okay. Um, of course, we know that generally speaking, right, you the duty of Fourier analysis is such that you feed it a periodic function, okay, and it outputs some of sines and cosines, okay? Sines and cosines, basically. So when you talk about these advanced tools, now we are looking at the possibility of even this Fourier analysis now taken beyond periodic functions to also include non-periodic functions, as beyond the normal, right? So non-periodic functions are now involved now that we talk about these advanced tools. And before now we had actually seen the use of Fourier transform in making this possible. So here we are still seeing some other theorems and transforms that are in that same line. Okay, let's move on to what we know as the Plancherel theorem. Plancherel theorem. Okay, so the Plancherel theorem, the Plancherel theorem states that the Fourier transform, it's just like I told you, Fourier transform actually the Fourier transform preserves the L2 norm, that's some real analysis term, preserves the L2 norm of a function. It preserves the L2 norm of a function. And what does this mean? So, which means the total energy, the total energy, and that total energy is given by the integral. It's given by the integral of the square, integral of the square of the function, integral of the square of the function is actually the same in both the time, in both the time and frequency domains, in both the time and frequency domains. Now, you remember that when we talked about Fourier transform, we discovered that for Fourier transform, right? Let me make the same analogy like I just did up there. So for Fourier transform, imagine you have Fourier transform here. So the analysis I did at the top is actually for Fourier series. This is more like for Fourier series to be more specific. But for Fourier transform, right? Fourier transform actually takes in a function, it takes in a function f of x in the time domain, okay, and outputs it as a function, a different function in the uh, frequency domain. So this function now is in the frequency domain. Okay, so that's the beautiful thing going on right here. Okay, um, then so but what this Plancherel theorem is telling us is that the function in this domain is actually the same here because the energy is preserved. So let's see how that looks in formal terms. So formally, um, for a function, for a function f of x, we have integral from minus infinity to infinity of the absolute value of f of x all squared dx. F of x all squared dx is equal to integral from minus infinity to infinity of f of omega squared d omega. Okay, so now again, we're talking about this being in the time domain. This is in the time domain, and the Fourier transform translates it to something in the frequency domain. And then what the Plancherel theorem is telling us is that the energy is preserved in both domains, basically. All right. So this theorem ensures that the Fourier transform, to ensure that the Fourier transform is a unitary operation, Okay. That's what the theorem basically does. So what that means is that preserving the energy, it preserves the energy of the signal, preserves the energy of the signal. And that is what we have for that. So the next thing, the next advanced tool, apart from the Plancherel theorem, is what we know as the wavelet transform. Wavelet transform. So let's see to that. We have the wavelet transform. So the wavelet transform, the wavelet uh, perfectionism is a problem. So the wavelet transform, okay, the wavelet transform is an advanced tool. It's an advanced tool for signal analysis. For signal analysis, particularly for signals that vary over time. For signals that vary over time. Okay. Now, unlike Fourier series, unlike Fourier analysis, which provides global frequency information, which provides global frequency information, the wavelet transform, gives both time and frequency localization, both time and frequency localization, making it ideal for non-stationary signals, making it ideal for non-stationary signals. Okay, Now let's take an example as we wrap that up. So example. So the Morlet wavelet is commonly used in time frequency analysis. In time frequency analysis, and can be applied to decompose a signal into both time and frequency components, offering better localization for transient signals. Okay, transient signals than traditional Fourier analysis, Okay. Yeah, with this I come to the end of this video. But just like I said, of course, the playlist on sequences and series actually continues after now, because there are still other things to talk about, like generating functions and the rest of them. So you want to subscribe to this channel and hit the notification bell so you can always get alerted each time a new video is released. You also want to comment to let me know how helpful these videos are, and if you want me to teach a topic or solve a problem, then you also want to like and share so that more people can have access to this great content. By the way, I have another playlist on scientific computing with Python. So along the line, I'll be talking about fast Fourier transform. So they'll be using Python code to, see what the capabilities of Fourier series, and how maybe in real time how it works with image processing, signal processing, and the rest of that. So you don't want to miss out on any of these things. So hang around and watch out for these things. Bye.